Hey everybody, in this video we're going to write the rate law for the reaction of C plus D turns into E using this method called the method of initial rates. Let's get started. First thing you got to do is compare any two of the experiments given where only one of the reactants has a different concentration. We'll find that first between experiments 1 and 2. So we're going to compare those. And I like that one because the concentration of C is the same in both of those experiments. The concentration of D is the only one that changes, and it changes by a factor of 2, so we're going to make a note of that. This is helpful because now I'm going to go over to the initial rate of the reaction and see what effect that doubling of D's concentration has on the rate. We can see that the rate also changes by a factor of 2. Anytime the change in molarity is the same as the change in the rate, so here they both changed by a factor of 2, then that means that that reactant is first order. Another way to do it mathematically is to take the two changes. In this case, they both changed by 2. And asking yourself, 2 to what power gives me 2? Of course, 2 to the first power gives me 2. The point of this is that D is first order. At this point, I'm going to start building out the actual rate law itself. Rate equals lowercase k is the standard format, multiplied by the concentration of the two reactants. C, which I don't know yet, but also D, which I do now know, is first order, so I can put in an exponent of 1. So now we've got to do that again, but instead try and find two experiments where reactant C is the only one that changes. We can find that between experiments 4 and 5, because in 4 and 5, D is the one that stays constant, and here C is the only one changing, and again by a factor of 2. So we're going to do the same thing and go over to the rate and see what its change is. And then interestingly, you'll notice that in this case, the rate does not change at all. Or if you want to actually think about it, it changes technically by a factor of 1. When you see this happening, when a reactant's concentration changes, but that concentration change does not affect the rate, you are seeing that that reactant is something called zeroth order. Yes, that is an option. So here reactant C has to be zeroth order. Zeroth order just means that that particle's concentration has no effect on the rate. We could make C's molarity whatever we want, and the rate will go completely unchanged. It even works mathematically if you want to use the same little trick we did up here. Pull out the two changes. In this case, it was a change of times 2 and a change of times 1. And ask yourself, 2 to what power gives me 1? 2 to the zeroth power would give me 1. So both ways will work to get the order of the reaction. We can also rewrite the whole rate law at this point. Instead of including C in there, you could remove C altogether because anything raised to the zeroth power is of course 1. So it is, in essence is fully removed from the rate law, which also makes sense because again, C's concentration does not affect the rate, so it doesn't need to be in the rate law at all. As far as the overall reaction order, we can add up the 0 for C and the 1 for D to get a overall reaction order of first order. We can also now solve for the value of K and include appropriate units by plugging in numbers from any of these experiments into the rate law that I just wrote. So let's use experiment 1 for that because that's what is usually easiest. And for the rate, we'll plug in 0.02 because that's the rate in experiment 1. The K value is what I'm solving for. C doesn't matter because it's not in the rate law anyway, so it's really just the concentration of D, which is 0.01 to the first power. And if you rearrange and solve for K, you'll get an answer of 2. So that's just the value of K. We also need the units on K, and K values rate constant Ks, they can have all kinds of different units depending on the reaction order. If you don't know the units of a first order reaction, you can always solve the rate law again, but this time using units, moles over liter seconds for rate. K value is what I'm solving for, and the concentration is of course always moles over liters to the first power. So again, we're just solving this, but now for units and rearranging them rather than with an actual number. Here we would multiply both sides by the reciprocal to cancel this off, leaving us with K equals. So we got to multiply this side by the same, liters over moles. Here you're going to have some things canceling off, like liters will cancel because that's in the top and the bottom of the fraction. Moles will do the same thing. So all we're left with is seconds in the denominator, which you could write as 1 over seconds. And sometimes you'll see that expressed as seconds to the negative 1. So our official answer for part C is the rate constant is 2 seconds to the negative 1. That wraps it up for this video. Thanks a lot for watching.